Hello, everyone. So, in this lecture, we're going to be looking into quantum mechanics and what all it entails. So, in the PowerPoint slides, we're going to be picking up on the one that pertains to Schrodinger's model. And so that's where we're going to start at. But really, in all honesty, the quantum mechanics, the whole model is based around Schrodinger's equation, which ultimately looks at hydrogen and its wave functions in detail. So, so what is Schrodinger's model? Schrodinger developed a model, a mathematical equation that helps to explain and describe the path that electrons take. And this model, this equation that you see, is that it's actually shown right here where my mouse is. This is the basis for what we're going to be looking at in terms of quantum mechanics. So we won't be worried about any mathematical calculations that involve Schrodinger's equation. That's something that you'll learn later. So now the path that these electrons take, there's possibilities and probabilities of where they will be found. And so now we did look at Bohr's model back in the beginning and in the previous slides for this PowerPoint, and we saw how the electrons are placed into discrete energy levels. But there's a little bit of difference here in relation to what Bohr's model states versus Schrodinger's model in terms of quantum mechanics. So again, Bohr placed them in discrete energy levels, and whereas Schrodinger calls them orbitals and places electrons in the most probable place that they can be found. And that's really the thing that you have to understand is, where are the electrons to be found? So you take this atom, and this is the nucleus of the atom. You have the electron cloud that goes around it from here to here. So you take hydrogen, which has one electron. Well, where's that electron going to most likely be found? What's the most probable place? It's like drawing a dartboard, and you have your bullseye in the middle. And so as you throw your darts, most of the darts are going to be found most towards the center. But then there's going to be some random ones that are found towards the outside. But the most probable place it's going to be found is where the more dense packed holes are going to be in a dartboard, which is going to be towards the center of it. So you would expect the electron to be most probably found in that position. Now, in quantum mechanics, we also have to pay attention to the quantum numbers. And so there are 4 quantum numbers that we're going to be looking at. And here's the first one. So this first quantum number is given the symbol n, and it's related to the size and energy of the orbitals, and it could have values that range between 1 and 7. Now, we won't be using anything higher than 4, and I'll explain to that in just a short bit, but there's possibilities it can go on up as high as you really want to go. But reality is that we live here on Earth, and Earth has only a certain number of elements. All right. Now the second quantum number that we're going to look at is called the angular momentum quantum number, and it's given the symbol L, and it should be cursive. All right. So this here is here. It's related to the shape of the atomic orbitals, and so now, as you can see here, that it ranges from 0 to n minus 1. And so we start off with S being 0, and then you have P is 1, 2 is D, 3 is F, and so on and so forth. All right, and so these shapes are important in terms of where the electrons can be found, the most probable place that they can be found. So when we deal with an s orbital, the shape is this spherical shape that you see here. And all right, the P is found right here, and all it is just like a dumbbell. I think of a dumbbell, and you're lifting weights. So if you're puny, you go lift weights in the gym, and that's how you get strong. Now the last one that's on in the picture is the D, and it's represented by the 4 lobes that you see here. Now pay attention to the middle, and this will be something we look at a little bit later on, but pay attention to the middle because the middle has nothing. It's those lobes are not actually contacting each other. They're separated. Why do you think that is? What do you think the reason for there being an absence here in between? Now you can't see it in the s orbital because it's completely enveloped inside of it, but still there. Now the third quantum number is the magnetic quantum number, m sub L, and it's related to the orientation of the orbital. So remember that in a 3-dimensional world, you have x, y, and z planes, and these orbitals have to exist in a 3-dimensional world, so they adopt that same type of configuration. So that you have to understand and learn, basically know what directions these orbitals are oriented in, whether it's an XY plane, a Z plane, an X, etc. And that's something we'll look at in a little bit more detail later into this PowerPoint. So, but for now, it's just something that we're learning. So the symbol for the magnetic quantum number is m sub L. So, and again, the L should be a cursive L, as you see here. So now this blue chart that you're looking at has all 3 of those quantum numbers that we have been discussing. And so you can see that you have the N, which is your principal, ranging between 1 and 4. And then if you look at L differs within each one. And we're going to talk about that. And then m sub L follows the L in this particular case. So now let's say that we have n equals 1. All right. So we asked the question, so if your value for the principal quantum number is 1, what would be the value for your L? Well, L is always n minus 1, which in this particular case, 1 minus 1 equals 0, so your L will be equal to 0. And that's where that n minus 1 comes into play. The n represents the principal quantum number, and that's how you determine your L value. So it's just simply making sure you understand the pattern. So you have your n, you've got your L, which is always n minus 1, so L and n will never be equal to each other. And then you get your m sub L value. Your m sub L value is going to be related to your L value. And so, well, since L is equal to 0, there's no range between 0 because 0 is 0, so your m sub L is equal to 0. Now that's just one example where you have n equals 1. So let's say that you have n equals 3. All right, now your L value, the first one that you ought to come up with would be 2 because n minus 1 is 2. And then it just goes down from there, and it goes down to 0 because it's always n minus 1. Now, as we look at the m sub L values, okay, so the m sub L values, they become a little bit more involved for this. Now, you pay attention to the value that your n equals 3, then you got L's 2 and 1 and 0. So let's start off with L is equal to 0 because we know what that is. It's 0. All right, there's no range between 0 because it's 0. But for 1, L is equal to 1, the range is going to be minus 1, 2, plus 1. And then for L is equal to 2, it's going to be minus 2 to plus 2. All right, and that's the pattern that you see here. All right, so if we look at at this box here, you have 0, which represents an S shell, and that means that your m's of L is 0, because L is equal to 0, m's of L is equal to 0. Now, if your L is equal to 1, that represents a 3p orbital, and then the range is like we just said, at -1 to +1. And if you look at 2, 2 is -2 to +2. All right. So notice that we're also pay attention to the type of orbital that we're looking at. So 0 is S, 1 is P, and 2 is D. Okay. So now if you look at 4, n equals 4, the range is between 0 and 3, 0, 1, 2, and 3 for L. All right. So we're just adding in another shell here because you have that extra L value there, which is 3. All right, now 3 represents a 4f orbital, and there are -3 to +3 range. So the pattern is going to be always, you've got your n, L is equal to n minus 1, and then your m's of L is the range between whatever L value it is that you're looking at. Now, the other part that I want to just kind of point out to you is the number of orbitals that you see for each of these shells that I'm calling them. So let's say that you are a 2p orbital, all right, and the value of n, well, it can range, and it can be several of those, right? So if your L is 2, that means your m's of L is going to be -2, -1, 0, +1, and +2. So the number of orbitals represents the sum of all the m's of L's, which you don't really add -2 plus -1 plus 0. You just count the numbers. So 1, 2, 3, 4, 5. So there's 5 total orbitals for your m's of L for L's 2. All right, so there's 5 orbitals in the m's of L category for L is equal to 2. Now, what if L was equal to, let's say, 5? All right, so 5, you'd have 5, -5, -4, -3, -2, -1, 0, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you'd have 11 total orbitals for L equal to 5. But there is no such thing as L is equal to 5 because that goes beyond what we would see in our course. And even on Earth, Earth doesn't have that many elements. So, okay. Now, I want to just kind of point this out. Let me go ahead and just get this other stuff erased here. So we're going to talk about the Heisenberg uncertainty principle here. So Heisenberg uncertainty principle states that there is a fundamental limitation to how precisely both the position and momentum of a particle can be known at a given time. So you can't know the place and time all at the same point. You can't do it. You might need a location, but you don't know when it's going to get there. You might know it's going to get there, but you don't know where it's going to be. That's all Heisenberg uncertainty principle states. And think about that for a second. Think about how small the electron is. Think about how fast the electron is moving. There's really no easy way to solve for two variables at the same time. And when we go back and you look at Schrödinger's equation is based around two variables, distance and time. And so you can't integrate over two things at once. You can't solve for two variables at the same time. So that's why Heisenberg's uncertainty principle plays an important role here, that you don't know one versus the other. You don't know at the same time. You can know one and not the other. Okay, that's all we need to know from that. All right, so again, the Heisenberg uncertainty principle states that there's that limitation between knowing how precise in both position and momentum particle can be known at a given time. So let's look at a couple examples that involve using these quantum numbers that we've looked at. So first example is an electron is determined to have a value of 2 for its angular quantum number. What are the possible quantum numbers it could have? Now, the first thing that you need to do in answering this is knowing what the angular quantum number represents. Now, going back to what we talked about, the first one was principal, the second one was angular, and the third one was magnetic. So another word for angular is azimuthal. So you'll see this word in some problems that you may encounter. So azimuthal is M-U-T-H-A-L. That's how you spell the last little bit of that. Is the L value. So L is equal to 2. So what are the possible quantum numbers it could have? Well, looking at N, well, if it's always L is net N minus 1, well, that means L is going to be plus 1, so it could be 3. All right, so that's the first possibility. And then 4, well, we know 2 and 1 are out. They're gone because they'll never be equal to 2 for your L. And then your M's of L value, well, L is equal to 2, so that's minus 2 to plus 2 for the possibility there. So another possibility could be minus 3 to plus 3, because that would give you 2 if you needed it to be. So, but for all logistics purposes here, what really is important is knowing that your N value has to be 3 or 4, so that way your L can be equal to 2. All right, so that's where that comes into play. All right, so now the next question is, could an electron occupy both N equals 1 and L equals 1 at the same time? Well, let's go back to the value that the fact that we talked about N earlier as being 1, and then your N, your L is always going to be N minus 1. So your L is going to be equal to 0. So no, this is not possible. All right, so it's not possible because of this reasoning. If you wanted to make it a possibility, then your N can't be 1. It's going to have to be 2 or higher, 2, 3, or 4. All right, so that's where that comes into play yet again, is knowing that how you utilize these different quantum numbers and knowing the individual rules for each of those. So that's where you come into the different examples, and knowing that N is your principal quantum number, L is your angular azimuthal quantum number, and then M's of L is your magnetic quantum number. Again, that the magnetic is how it spins on the different axes, X, Y, and Z. So electron probabilities and shapes of the orbitals. Now we've looked at 3 of these shapes already. So an orbital can be considered as a charged cloud when a specific region contains a percentage of the electron's charge, because electrons are negatively charged, and that's why it's considered a charged cloud, where the electrons are predicted by geometric pictures of the orbitals, and all orbitals with the same value of N have the same energy are said to be degenerate. So that's not possible. All right. So let's look at this S orbital. All right. So S orbitals again have this spherical symmetry. The size of the orbitals really depend on the value of N itself. Remember that N can be ranging from 0, 1, 2, 3, and 4. That's what we looked at. And so it's like an onion. Basically, onions have layers. So you start off with the very beginning, the 1s that you see here, and then if you add in a second shell, it then surrounds that, and then if you add in a 3, S shell, you surround that, and the fourth one would be around it. Now, in each case, you have these nodes that form. All right, nodes are a no-go zone. All right, and the electrons are not going to exist where a node is. All right, again, it's a no-go zone. Now, the next orbital is the p orbital. Again, we talk about the fact that they have dumbbell shapes, and these dumbbell shapes are related to how they're arranged on the x, y, and z planes. And so you can see that there are three possibilities. Now, if you go back and you think about, the number of orbitals in that blue chart, your L0 is an S shell, and there's only one orbital because you only count 0 once. Then you go to L is equal to 1. Well, L is equal to 1. You have -1, 0, and +1. So that's 3 possibilities. And so if you look at that, so this is the reason why, is because you have one possibility on the z plane, one on the x, and one on the y. So you have 3 different possibilities of where the electrons can be existing. Now, the other thing I wanted to point out to you is that earlier I asked you about the middle of these lobes. Why is it empty? Well, anybody have anything to say about why do you think that it's empty? Can an electron exist in the middle here? And the answer is no. And you say, well, why? It's because the nucleus is there. The nucleus is occupying that space, so no electron can exist there. The electron can only exist in the electron cloud, which is around the nucleus. You're probably always thinking, duh, that makes sense, right? Now, the d orbital has 5 different possibilities. We looked at that. So remember, there's a pattern. So you have 0 is 1 orbital. 1, L is equal to 1, has 3 possibilities. Now D, which is 2, has 5 possibilities. So there's a pattern, 1, 3, 5. And if you go up another one, it would be 7. Now, I'm not asking you guys to memorize the orientations about these. All we're trying to understand is that there are 5 possibilities, 5 orbitals, 5 possibilities of where electrons can exist for that D shell. All right. Now, the last one is, and this is the quantum number 4, where you're going to have your L is equal to 3. This is an f orbital, and an f orbital has 7 possibilities. And that, again, it's that pattern that you see there, 1, 3, 5, 7. So those are how the electrons are arranged amongst the possibilities of where the electrons can be found based off the principal quantum number, the angular quantum number, and then the magnetic quantum number. Now, the 4th quantum number is called the electron spin, and it's represented by this symbol here, m of s, and it's related to how the electron spins on the axes. All right. So we know that the electrons themselves are all negatively charged, and this negative charge plays a big role within how we see the electron spin. When you put 2 electrons beside each other, you're going to see some repulsion take place. So really what happens is, to minimize this repulsion, the electrons spin in opposite directions. So you have this plus 1/2, and you have this minus 1/2. If you've ever done electron configurations in high school, you probably saw the electron configurations, 1s2, 2s2, 2p6, etc. And this all ties right back into that and why that takes place. So that's the fourth quantum number. Now, to go along with the fact that the electrons do have these half spins, the next thing we have to understand is that an orbital can only hold 2 electrons at one point in time, and that's because the 2 electrons are going to have opposite spins, that plus and minus 1/2. So that's an important detail, especially when we get into electron configuration. Now, the last thing we're going to talk about in this particular video is the Pauli exclusion principle. It states that in a given atom, no 2 electrons can have the same set of 4 quantum numbers. So they're never going to be the same. So you can't have one atom, one element having the same configuration as the second element that would be present. They're going to have 2 different sets of quantum numbers. They can never be the same. Now, the last comment I want to make here is that this chart here is an important chart to either memorize or just learn and understand, because you don't really need to be going back and looking at this when it comes time for the test. This is actually fairly easy material as long as you understand the basics and the patterns that you see here. Now, if you ever come into a situation where you're talking about, a ground state versus an excited state, like we talked about in the previous lecture videos, what you ought to understand now is that when you talk about ground state, a ground state might have this configuration, and it's possible. So notice that the value of the n value is 1, your L is 0, and your M's of L is 0. That's in the very most basic state. When you get away from 0, you start to become in a more excited state. Therefore, that's why we call it ground versus excited state. Another configuration bit equals 2, L is 0, and M's of L is 0. So that's another configuration. But the important thing to remember here is that when you have these zeros in sequence like this, that gives you an indication that you're working with a ground state configuration. So now we're going to next get into electron configurations. That will be a separate video from this. So, that's all I have for quantum mechanics. Thanks, guys.